somewhere out in the Milky Way, there is a small, ordinary yellow-white star. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. That star sits roughly 26,000 light years from the center of our galaxy, tucked quietly inside one of the Milky Way's spiral arms. It is not the biggest star. It is not the brightest. Among the hundreds of billions of stars in our galaxy alone, it is, in almost every way, unremarkable. And yet, it is the reason you are here. That star is our sun. And right now, at this very moment, it is burning through about 600 million tons of hydrogen every single second. That fuel powers every sunrise you have ever seen. It warms the oceans. It drives the winds. It pulls the light through the leaves of every tree that has ever grown on this planet. The sun has been doing this for about 4.6 billion years, and for most of that time, it has barely changed at all. But the sun will not burn forever. Every star in the universe lives by a kind of balance. On one side, gravity pulls inward, always trying to crush the star down into itself. On the other side, the energy from nuclear fusion, the process where hydrogen atoms are pressed together to make helium, releasing enormous heat and light, pushes outward. These two forces hold each other in check. The star neither collapses nor explodes. It simply glows, steady and patient, for millions or billions of years. Our sun has about 5 billion years of hydrogen fuel left. That is a number so large it is almost impossible to feel. 5 billion years ago, the sun did not exist yet. The Earth did not exist. The solar system was still a swirling cloud of gas and dust. In 5 billion more years, the universe will be more than twice as old as it is today. The scale of a star's life makes human history feel like a single breath. But here is what makes this story worth telling. When the hydrogen finally runs low, the sun will not simply flicker out like a candle. It will transform. It will swell into something almost unrecognizable. It will grow so large that it could swallow the inner planet's whole. Its surface will cool and shift from white-yellow to a deep, glowing red. It will become what astronomers call a red giant, a star in the last great chapter of its life. This transformation is not unique to our sun. Stars of similar size and mass all follow this same path. They burn their hydrogen, they swell, they glow red, and they slowly shed their outer layers into space. It is one of the most common endings in the universe, and it is, in its own quiet way, one of the most beautiful. The gas and dust that a dying star releases does not simply vanish. It drifts outward into space, cooling slowly, carrying with it all the elements that star spent its life creating. Carbon, oxygen, nitrogen, the raw material for new stars, new planets, and new possibilities. The death of one star plants the seeds of the next generation. Everything connects. Everything continues. Tonight, we are going to follow that story from beginning to end. We will start here, with the sun as it is right now, steady, warm, and full of fuel. We will watch it age. We will see it swell into a red giant, enormous and slow, and dimly glowing against the dark. We will follow it through its final stages, through the quiet shedding of its outer layers, until all that remains is a small, dense, cooling ember called a white dwarf. It is a long story. It spans billions of years and reaches across distances that no human mind can truly picture, but told slowly, told gently. It is also a deeply peaceful one. Stars are not in a hurry. They burn and they change, and they fade across timescales so vast that even the word slow does not quite cover it. So settle in. Let your breathing slow. The universe has been telling this story for as long as stars have existed, and it will keep telling it long after our own sun has gone quiet. Right now, that sun is still shining, still burning, still holding the planets in their orbits with steady, patient gravity. It is doing exactly what it has always done. For now, everything is as it should be. The sun is a star. That simple fact is worth sitting with for a moment. That warm light on your face on a summer afternoon, that is starlight. The same kind of light that reaches us from thousands of other stars scattered across the night sky. Our sun is one of them, just one. And yet, to us, it is everything. Stars come in many sizes and colors, Some are enormous, burning blue-white and fierce, many times larger than our sun. Some are tiny and dim, barely glowing red in the dark. Our sun sits comfortably in the middle of that range. Scientists call stars like it solar-type stars or sun-like stars. These are stars that share a similar size, a similar temperature, and a similar mass, meaning a similar amount of material packed into them. Mass is one of the most important things about a star. Think of it as the star's weight, though in space, weight works differently than it does here on Earth. A star's mass decides almost everything about it. How hot it burns, how long it lives, and how it dies. Sun-like stars have a mass roughly between half and twice the mass of our own sun. That range might sound wide, but in the full scale of stars in the universe, it is a fairly narrow group. Our sun's mass is almost impossible to picture directly. It contains more than 99% of all the material in our entire solar system. Every planet, every moon, every asteroid and comet and speck of dust, all of that combined makes up less than 1% of the total. The sun holds the rest. It is, by a vast margin, the dominant object in our neighborhood of space. The sun sits about 93 million miles from Earth. Light, which travels faster than anything else in the universe, takes about 8 minutes to cross that distance. So when you look at the sun safely, through proper protection, you are seeing it as it was 8 minutes ago. That is actually a very short delay compared to other stars. The next nearest star to our sun, a small dim star called Proxima Centauri, is so far away that its light takes more than 4 years to reach us. Our sun is about 4.6 billion years old. That number is so large, it loses meaning quickly. So here is one way to feel it. If you compressed the entire history of the sun into a single calendar year, human civilization would appear only in the very last second of December 31st. The sun was already ancient before the first humans ever looked up at the sky. And yet, by the standards of its own lifespan, the sun is middle-aged. Scientists estimate it has roughly another 5 billion years of steady burning ahead of it before things begin to change. It is not young, but it is far from finished. is in the most stable phase of its life, a long, quiet stretch that astronomers call the main sequence. That simply means the star is doing what it was built to do, burning steadily and holding its shape. The sun is made mostly of hydrogen, the lightest and most common element in the universe. About 73% of its mass is hydrogen. Most of the rest is helium, the second lightest element. Everything else, oxygen, carbon, iron, all the heavier elements, makes up less than 2% of the total. The sun is, in the most literal sense, a giant ball of gas, but it is gas under such crushing pressure and at such extreme heat that it behaves in ways that nothing on Earth quite matches. At the sun's core, temperatures reach about 27 million degrees Fahrenheit. At that heat, hydrogen atoms are stripped down to their basic parts and forced together in a process called nuclear fusion, where small atoms combine to form larger ones and release enormous amounts of energy. That energy is what we feel as sunlight and warmth. It is what has made life on Earth possible for billions of years. Sun-like stars are not rare. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. A significant portion of those are sun-like. Across the observable universe, the part we can actually see, there may be more sun-like stars than there are grains of sand on every beach and desert on Earth, each one burning, fusing, holding its own small family of worlds in orbit, following the same slow arc that our own sun is following right now. They are all telling the same story, just at different points in the telling. That story begins long before the first light, long before there is a star at all. Picture a cold, dark cloud drifting through space. Not a cloud like the ones we see on a summer afternoon. This is a vast cloud of gas and dust, spread across dozens of light years. It is mostly hydrogen, the simplest and most common element in the universe. It floats in the dark, nearly still, for millions of years. Then something disturbs it. Maybe a nearby star explodes. Maybe two clouds drift close and brush against each other. Whatever the cause, a small part of the cloud begins to pull inward. Gravity, that quiet and patient force, starts drawing the gas toward a single point. This process is called a nebula collapse, and it happens slowly at first. The gas falls inward over hundreds of thousands of years. As it falls, it heats up. Pressure builds at the center. The cloud begins to spin, flattening into a wide disk with a dense, hot ball forming at its heart. That ball is called a protostar, which simply means a star that is still forming, not yet fully born. For a long time, the protostar just sits there, glowing faintly, gathering more and more material from the disk around it. It grows hotter. It grows denser. The pressure at its core keeps climbing. And then, at some point, something remarkable happens. The temperature at the center reaches about 18 million degrees Fahrenheit. At that exact threshold, hydrogen atoms stop just bumping into each other. They begin to fuse. Nuclear fusion is the engine at the heart of every sun-like star. It is the process where two hydrogen nuclei, the tiny cores of hydrogen atoms, are pressed together so hard and so fast that they merge into a single helium nucleus. That merger releases a burst of energy. Do it once, and the energy is tiny, almost nothing. But inside a star, this happens roughly 600 million tons of hydrogen per second. The energy released is staggering. That energy pushes outward from the core in the form of light and heat. It takes a long time for that energy to travel from the core to the surface. In our sun, a single particle of light can take anywhere from 10,000 to 170,000 years to work its way from the core to the outer edge, bouncing and scattering through dense layers of gas the whole way. Then, once it reaches the surface, it crosses the 93 million miles to Earth in just 8 minutes. The moment fusion begins, the star is born. And from that moment, two forces enter into a careful balance. Gravity keeps pulling everything inward, trying to collapse the star. The energy from fusion keeps pushing everything outward, trying to blow the star apart. These two forces hold each other in check for billions of years. That balance is called hydrostatic equilibrium, which means the inward pull and the outward push are exactly matched. The star neither shrinks nor explodes. simply burns. For a sun-like star, This stable burning phase lasts an extraordinarily long time. Our sun has been fusing hydrogen for about 4.6 billion years. It has enough hydrogen left to keep going for roughly another 5 billion years. That is a total lifespan of about 10 billion years spent in this quiet, steady state. Larger stars burn hotter and faster, running through their fuel in just a few million years. Smaller stars burn so slowly and cool that they can last for trillions of years, far longer than the universe has even existed so far. Sun-like stars sit right in the middle, burning at a pace that is, in cosmic terms, steady and measured. The fuel itself is not unlimited. Every second that passes, the sun converts about 600 million tons of hydrogen into helium. The helium collects at the core, slowly building up like ash in a fireplace. The hydrogen supply, enormous as it is, does have an end, and the story of what happens when that end approaches is the story this whole episode is slowly moving toward. But for now, the star is young. The fire is steady. The light flows outward through billions of miles of space, warm and constant. Somewhere in the disk of gas and dust that surrounds the newborn star, small grains of rock and ice are beginning to clump together. Planets are forming, and on at least one of them, billions of years from now, creatures will look up at that steady light and wonder where it comes from. The answer is here, in a cold cloud, in a slow collapse. In the moment, two atoms touched and the darkness broke open. That helium building up at the core is not just a byproduct. It is the beginning of everything that comes next. For billions of years, the core of a sun-like star is a place of constant, furious fusion. Hydrogen atoms are pressed together under enormous heat and pressure until they merge and become helium. That process releases energy. That energy pushes outward, and that outward push is what holds the star up against its own crushing gravity. The two forces balance each other perfectly, and the star holds its shape, steady and round, for billions of years at a time. But helium does not fuse the way hydrogen does. Not yet. Not at the temperatures found inside a young, stable star. So as the helium forms, it simply sits there. It collects at the center of the core, dense and inert, doing nothing. Scientists call this growing heap the helium ash. And just like ash in a real fire, it slowly takes up more and more of the space where the fuel used to be. The hydrogen does not vanish all at once. It burns from the inside out. The very center of the core runs out of hydrogen first, because that is where the pressure and heat are highest. The fusion there stops, but hydrogen still exists in a thin shell just outside that dead center. So the burning shifts. It moves outward to that shell, like a grass fire spreading to new ground when the center has already burned through. The star keeps shining, but something has changed deep inside. The helium core, no longer heated by fusion from within, begins to compress under its own weight. Gravity never stops pulling. When the energy pushing outward weakens, gravity wins a little more ground. The core grows smaller and denser, and as it compresses, it actually heats up. This is one of the strange truths of stellar physics. Squeezing a gas makes it hotter. The core shrinks, and in shrinking, it glows with new heat. That extra heat radiates outward into the hydrogen shell surrounding the core, and a hotter shell burns faster. The fusion in that shell speeds up. More energy pours outward into the star's outer layers, and those outer layers begin to respond. This is the moment the star starts to change. Not dramatically, not yet. The change is slow, measured in millions of years. But the direction is set. The star that was once balanced, stable, and steady is now beginning a long, gradual shift towards something much larger and much cooler. The hydrogen that remains in that burning shell is still the same hydrogen that has always been there. It is the most common element in the universe. Roughly 3/4 of all the ordinary matter in existence is hydrogen. It was forged in the first few minutes after the universe began, in an event scientists call the Big Bang. Every hydrogen atom inside the sun, inside every star, inside every cloud of gas floating between the galaxies, traces its origin back to those first moments of existence. The helium is younger, in a sense. Some of it also formed in those first minutes, but the helium now building up in the core of a sun-like star was made right there, inside the star itself, over billions of years of steady fusion. It is new matter, built from old matter, transformed by heat and pressure into something the universe did not have before. This is one of the quiet miracles of stars. They are not just light sources. They are factories. They take the simple elements left over from the birth of the universe and forge them into new ones. The helium now sitting in that stellar core will eventually become something else entirely. Given enough heat, given enough pressure, helium atoms will fuse too. They will form carbon, and carbon is the backbone of life. The carbon in every living thing on Earth was made inside a star. Not our sun, not yet. Our sun has not reached the stage where it fuses helium into carbon, but older stars, stars that lived and died before our solar system even existed, went through exactly this process. They built carbon in their cores. Then they scattered it across space when they died. That carbon drifted through the galaxy for millions of years. Eventually, it became part of the cloud of gas and dust that collapsed to form our sun and our planets. Eventually, it became part of us. The helium now collecting in the sun's core is the first step in a chain that stretches across billions of years and billions of miles. The ash of one fire becomes the fuel for the next, and the next fire will change the star forever. Right now, deep inside the sun, something is shifting. It is slow. It is quiet. From the outside, you would never know. The sun looks the same as it always has, a steady, golden light hanging in the black. But inside, two ancient forces are moving toward a new balance. And that new balance will change everything. Those two forces are gravity and pressure. They have been locked together since the sun was born. Gravity pulls inward. It wants to crush the star down into a single point. Pressure pushes outward. It wants to blow the star apart. For billions of years, these two forces have held each other perfectly still. Scientists call this balance hydrostatic equilibrium, the state where a star neither collapses nor explodes, but simply holds its shape. It is one of the most stable things in the universe, and it is about to be tested. The test begins in the core. As hydrogen fuel runs out, the core slowly fills with helium ash. makes no energy, makes no outward pressure. Gravity, which never rests, begins to win. It squeezes the helium core tighter and tighter. The core shrinks. It grows denser. And as it shrinks, something remarkable happens. It grows hotter. This is a strange but true fact about gravity and gas. When you compress a gas, it heats up. You can feel this yourself if you pump air into a bicycle tire quickly. The pump gets warm. The same thing happens inside a star, just on a scale almost too large to picture. As gravity crushes the helium core inward, the temperature at the center of the sun will rise dramatically. Scientists estimate the core temperature will climb to tens of millions of degrees higher than it is today. The core becomes a furnace that no longer burns, but still glows with fierce, trapped heat. That heat has to go somewhere. It spreads outward into the layers of hydrogen gas that still surround the core. And here is where the first visible change begins. Just outside the dead helium core, there is a thin shell of hydrogen that has not yet been used. The rising heat from below reaches this shell. It ignites it. Hydrogen fusion begins again. But now it burns in a shell around the core, rather than throughout the whole center of the star. This shell burning is the spark that starts the transformation. It is the first sign that the sun is no longer the same star it once was. Shell burning produces enormous amounts of energy, more energy than the core fusion that came before it. That energy floods outward through the star's outer layers. The outer layers absorb this energy and begin to expand. Slowly, over millions of years, the outer envelope of the star puffs outward like a slow breath. The star grows larger, not all at once, not in any way you could watch in a human lifetime, but the process has begun, and it will not stop. Meanwhile, the helium core keeps contracting. It keeps heating. The outer layers keep expanding. The star is doing two opposite things at the same time, shrinking in the middle and growing on the outside. This is the quiet contradiction at the heart of a red giant's birth. The star is not exploding. It is not dying. It is reorganizing. The forces that shaped it are finding a new arrangement. There is something worth sitting with here. These forces, gravity, pressure, heat, are not rare or exotic. They are the same forces that shape clouds, that drive weather, that keep your feet on the ground. The universe uses the same simple tools everywhere. It just uses them at different scales and over different stretches of time. Inside a star, those tools work across millions of miles and millions of years. But the physics is the same physics. The rules do not change. The sun is roughly halfway through its life right now. It has about 5 billion years before these changes fully take hold. 5 billion years is a number that is hard to feel, but the process is already written into the laws of nature. The helium is already collecting. The core is already slowly contracting, degree by degree. The forces are already at work. What looks like stillness from the outside is, on the inside, a slow and steady turning. Like a wheel that has just begun to move, the sun is already on its way to becoming something new. And when that turning finally completes, the change in size is almost impossible to hold in your mind all at once. Right now, the sun is about 865,000 miles across. That is already enormous. If you placed the sun at the center of a football field, it would stretch from one end zone to the other and keep going. Earth, by comparison, would be about the size of a marble sitting somewhere in the bleachers. The sun already dwarfs everything in our solar system by a wide margin. And yet, what it will become makes its current size look modest. When a star like the sun exhausts its hydrogen fuel and the core begins to contract, the outer layers respond in a way that seems almost contradictory. The core shrinks and heats up, but the layers above it expand outward. They swell. They push away from the center in a slow, steady bloom that takes hundreds of millions of years to complete. By the time the process finishes, the sun will have grown to roughly 100 to 200 times its current size. Some estimates place it even larger, depending on how the final stages unfold. To feel what that means, go back to that football field. The sun fills it now, but as a red giant, it would swallow the entire stadium. It would swallow the parking lot. It would swallow the surrounding neighborhood for miles in every direction. The same star, the same mass, the same gravity, just spread across a volume of space so much larger that it barely resembles what it once was. Here is another way to picture it. If the current sun were shrunk down to the size of a basketball, Earth would be a small peppercorn sitting about 26 yards away. That is already a striking gap. Now imagine that basketball slowly inflating. It grows to the size of a beach ball, then a car, then a house, then a city block. By the time the sun reaches its full red giant size, that basketball would have swollen to something roughly the size of a large building. The peppercorn that is Earth would now be sitting inside it, or just barely at its edge, depending on how far the expansion goes. Scientists believe the sun will expand to somewhere between 100 and 200 solar radii. A solar radius being the current distance from the sun's center to its surface, about 432,000 miles. At 200 solar radii, the outer edge of the sun would reach nearly to the orbit of Earth. Some models suggest it may even briefly extend beyond Earth's current orbit before pulling back slightly. The exact boundary depends on how much mass the sun loses through its outer winds during this phase. And that is still something researchers are working to pin down more precisely. The expansion does not happen all at once. It is slow in a way that the human mind struggles to fully appreciate. The sun will spend hundreds of millions of years in the red giant phase, gradually growing, pulsing slightly, shedding material at its edges. From the outside, if you could watch it from a safe distance, it would look like a slow exhale, a long, unhurried release. What drives this outward push is the energy pouring out of the shell of hydrogen burning just above the contracting core. That shell produces more energy than the original core fusion did. More energy means more outward pressure. The outer layers of the star respond to that pressure by moving away from the center. They cool as they spread out. They thin. They become less dense. The star grows vast and diffuse, like a breath of warm air expanding into a cold room. This is the part that quietly astonishes. The sun is not gaining new material. It is not being fed from outside. The same atoms that make up the sun today will make up the red giant it becomes. Nothing is added. The star simply rearranges itself. The same mass, spread across a sphere hundreds of times wider, held together by the same gravity that has always been there. It is a kind of transformation that happens entirely from within. There is something deeply calm about that idea. The sun carries its future inside it right now. Every atom already present, every force already in place. The outcome is not uncertain. It is written into the physics of what the sun is. The expansion is not a crisis. It is a natural unfolding, as steady and inevitable as a seed becoming a tree. The scale of it is staggering, but the process itself is quiet, patient, and sure. As the star spreads outward, something remarkable happens to its surface. The outer layers grow cooler, and when something grows cooler, it changes color. This is not unique to stars. A piece of iron heated in a forge glows white, then yellow, then orange, then deep red as it cools. Stars follow the same rule. Temperature and color are linked always by the same physics. Our sun burns at roughly 5,500 degrees Celsius at its surface. That temperature produces the warm yellow-white light we see on a clear afternoon. But as a sun-like star expands into a red giant, its surface temperature drops. It falls to somewhere around 3,500 to 4,000 degrees Celsius. That is still extraordinarily hot by any measure we use on Earth. And yet, in the language of stars, it is cool. Cool enough to shift the color of the light it sends out. The star turns red, not a sharp, vivid red, not the red of a stop sign or a fire engine. It is something softer, deeper. Astronomers describe the color of red giants as ranging from orange red to a rich, dusty crimson, depending on the star's exact temperature and what elements float in its outer atmosphere. If you could drift in space and look at one from a safe distance, it would glow like an ember, like the last light of a fire settling into coals. Warm, enormous, and quietly radiant. This color shift is not just beautiful. It carries real information. Astronomers use a star's color as a thermometer. They call this relationship between color and temperature a star's spectral class. red giants fall into what scientists label as K-type or M-type stars, meaning they sit on the cooler end of the stellar color scale. By reading the color of a star's light, scientists can calculate its surface temperature with remarkable precision, even from thousands of light years away. The surface of a red giant is not smooth or still. It churns. Deep convection currents, which are slow rolling movements of hot gas rising and cooler gas sinking, move through the outer layers of the star. These currents are enormous. On the sun today, convection cells called granules cover the surface like a packed mosaic of bubbles, each one roughly the size of Texas. On a red giant, individual convection cells can span a significant fraction of the entire star. Some scientists believe a single convection cell on a large red giant could be wider than the distance from the sun to Earth. Imagine floating above that surface. The light coming up at you would be dim compared to what you'd see near our sun. Red giants are cooler, and cooler surfaces produce less intense visible light per unit of area. The glow would feel more like standing near a massive, slow-burning hearth than standing in direct sunlight. The surface would ripple and shift beneath you. Vast, slow movements of gas rising and falling across distances that dwarf entire planets. The atmosphere of a red giant is also extraordinarily thin and spread out. The outer layers of the star are so diffuse, so loosely held, that the boundary between the star and the space around it becomes almost soft. There is no hard edge. The star fades gradually into the surrounding void. Gas and dust drift away from the surface in what scientists call a stellar wind, a slow but steady stream of particles flowing outward into space. Red giants lose mass this way, gently, continuously, like a candle releasing smoke into still air. This stellar wind carries something precious. As the star expanded, nuclear reactions in its interior created new elements: carbon, nitrogen, oxygen. Some of these elements drift up through the convection currents and reach the surface. Then the stellar wind carries them away. The star is, quietly and slowly, seeding the space around it with the raw ingredients for future worlds. The color red, in this context, is not a sign of danger or ending. It is a sign of change. The star is doing what stars do. It is processing, releasing, transforming. The red glow of a giant star is the visible record of that work. Every photon of reddish light traveling outward from that surface has been shaped by millions of years of nuclear history deep inside the star. When you look at the night sky and find a star with a distinctly reddish hue, you are seeing this process from across the galaxy. Stars like Aldebaran in the constellation Taurus, or Arcturus in Boötes, glow with exactly this warm, ruddy light. They are red giants, caught mid-transformation, broadcasting their temperature and their age in every direction across the dark. But knowing a star glows red is only the beginning. The color tells you the temperature of the surface. What lies beneath that surface is a different story entirely. Red giants are enormous, not just large in the way that planets are large, or the way that mountains feel large when you stand at their base. We are talking about a scale that the human mind was not built to hold. Our sun right now stretches about 865,000 miles across. That is already so wide that more than 1 million Earths could fit inside it. And yet, compared to a mature red giant, our sun is modest. A typical red giant swells to somewhere between 10 and 100 times the sun's current diameter. Some grow even larger than that. Picture it this way. If our sun were to expand to the size of an average red giant, it would swallow Mercury whole. It would swallow Venus. Its outer edge would push past Earth's orbit and continue outward. The space where we live, where our blue planet turns slowly in the light, would exist inside the star itself, and that is only an average red giant. The largest red giants belong to a class called red supergiants, which form from stars much more massive than our sun. But even among ordinary red giants, the upper end of the scale is staggering. Stars like Myra, a well-known red giant in the constellations Cetus, Pulse, and Swell, until they reach roughly 400 times the sun's diameter. If Myra sat where our sun sits, its surface would extend past the orbit of Mars. Now go deeper. Beneath that vast, glowing surface The structure of a red giant is layered like an onion, each layer doing something different. The outermost layer is the envelope, the enormous shell of hydrogen gas that has puffed outward as the star expanded. This envelope is huge in volume, but surprisingly thin in density. The gas here is so spread out that it is, in some regions, thinner than the best vacuum humans can create in a laboratory. You could pass through the outer layers of a red giant and barely notice the material around you. It is more like a very hot fog than anything solid or even liquid. Deeper in, the envelope gives way to a churning zone called the convection zone. This is where hot material rises from below, cools slightly, and sinks back down, only to be heated again and rise once more. It is a slow, continuous rolling motion, like the surface of a very thick, very hot soup. This motion is what carries newly made elements up from the deep interior toward the surface, where the stellar wind can eventually carry them away into space. Below the convection zone, the temperature climbs sharply. The pressure climbs too. The gas here is no longer thin. It is dense and hot and packed tightly together. This is the radiative zone, where energy moves not by churning and rolling, but by being passed from one particle to the next, like a whisper moving through a crowd. A single packet of energy can take thousands of years to travel from the deep interior to the surface this way. And at the very center, there is the core. In a red giant at this stage of its life, the core is no longer burning hydrogen. That fuel is gone. The core is now a dense, hot ball of helium, the ash left behind by billions of years of hydrogen fusion. This helium core is incredibly compact. It is roughly the size of Earth, even though the star surrounding it stretches hundreds of millions of miles across. The contrast is almost hard to picture. A tiny, dense, Earth-sized ball of helium sitting at the center of a cloud of gas, so wide it would swallow planets. The core is not yet burning. It is contracting slowly under the weight of everything above it. As it contracts, it heats up. This is the stored energy of gravity being converted into heat. And it is this process that powers the hydrogen shell burning just outside the core, which in turn drives the expansion of the outer layers. Everything connects. The collapse at the center drives the swelling at the surface. The star has become a machine of opposites. Its outer layers drift outward, loose and cool and red. Its inner core pulls inward, dense and hot, and building towards something. What that something is will come later. For now, the red giant holds this tension inside itself, enormous and glowing, broadcasting its warmth across the dark in every direction. That warmth travels outward in all directions. It reaches the planets that have orbited this star for billions of years. And for those planets, everything is about to change. Think about what a solar system looks like at this stage. The star sits at the center, enormous and red. Around it, the planets move in their slow, steady circles. They have been doing this for a very long time. Billions of years of orbit, season after season, revolution after revolution. The rhythm of a solar system is one of the most reliable things in the universe. And yet, when the star at the center begins to swell, that rhythm starts to shift. The innermost planets feel the change first. These are the small, rocky worlds closest to the star. As the red giant expands, its outer edge creeps outward across space. The planets that once sat at a comfortable distance now find themselves much closer to the surface of the star. In some cases, they find themselves inside it. Mercury and Venus, in our own solar system, are almost certainly doomed this way. When our sun expands into a red giant roughly 5 billion years from now, it will grow large enough to swallow Mercury completely. Venus will likely follow. These two worlds, which have orbited the sun since the beginning of the solar system, will simply cease to exist as separate objects. They will be absorbed into the outer layers of the expanding star. The heat will strip away any atmosphere they still have. The rock itself will vaporize. What was once a planet becomes part of the star. This process is not a violent explosion. It is slow. The expansion of a red giant takes hundreds of millions of years. The planets do not disappear overnight. They are gradually overtaken, the way a tide slowly covers a beach. First, the heat increases. Then, the light becomes overwhelming. Then, the surface of the star reaches out and swallows them whole. survive this process face a different kind of change. The outer planets, the ones that sit farther from the star, are not consumed. They are transformed. As the red giant grows, it sheds material from its outer layers. This is a slow, steady outflow of gas and dust, carried away from the star by pressure and heat. Scientists call this a stellar wind. It is not like wind on Earth. It is a stream of particles flowing outward through space at tens of thousands of miles per hour. This stellar wind carries mass away from the star. And as the star loses mass, something interesting happens to the orbits of the surviving planets. When a star loses mass, its gravitational pull weakens slightly. A planet in orbit around a less massive star will naturally drift outward to a slightly wider orbit. This is a slow drift, almost impossible to notice over a human lifetime. But over millions of years, the outer planets of a red giant system gradually spiral outward, moving away from the expanding star. So the solar system breathes. The inner planets are consumed. The outer planets drift farther out. The whole system reorganizes itself around the new reality of a much larger, much less massive star. It is a kind of slow reshuffling, a new arrangement born from the old one. The moons of outer planets may be affected too. Some scientists believe that as outer planets drift to wider orbits, their moons can shift position as well. The gravitational relationships between a planet and its moons are sensitive to changes in the star's mass. A moon that was once locked in a stable orbit might find itself in a slightly different position after millions of years of these slow adjustments. And then there is the question of ice. The outer regions of a solar system, far from the star, are normally very cold. Water exists there as ice, locked into comets and frozen moons. But as the star swells into a red giant, the zone of warmth expands outward. Regions that were once frozen begin to thaw. Icy moons that were once locked in deep cold might find liquid water forming on their surfaces for the first time. This warming does not last forever. The red giant phase is temporary on a cosmic scale, but for a window of time, the outer solar system becomes a warmer, wetter place. Everything in a solar system is tied to to the star at its center. The star's light, its heat, its gravity, its mass. When the star changes, the whole system changes with it. The planets do not orbit in isolation. They are part of something larger, something that breathes and shifts and transforms over billions of years. The cycle of the star is the cycle of the entire solar system. Earth has been here for a very long time. It formed about 4.5 billion years ago from a swirling cloud of gas and dust. It has survived asteroid impacts, ice ages, and the slow drift of its continents. But Earth is not permanent. Nothing in the solar system is. And when the sun begins its long transformation into a red giant, Earth will feel every stage of that change. It starts long before the sun actually swells. Even now, the sun is slowly getting brighter. Stars like the sun grow more luminous over time as they age. Scientists estimate that the sun is about 10% brighter today than it was when Earth first formed. Over the next billion years or so, that brightness will keep increasing. The extra heat will slowly warm Earth's surface. Oceans will begin to evaporate. The water vapor will rise into the upper atmosphere, where radiation from the sun will break it apart. Hydrogen will escape into space. Over a very long stretch of time, Earth could lose its oceans entirely, long before the sun ever becomes a red giant. This is not a sudden event. It happens over hundreds of millions of years. But the direction is clear. Earth's window as a living, water-covered world has a limit. Scientists believe complex life on Earth may have somewhere between 500 million and 1 billion years remaining before the heat becomes too much to bear. That sounds like a vast stretch of time, and it is. But measured against the full life of the universe, it is a relatively short chapter. Then comes the red giant phase itself. When the sun finally expands, it will grow to perhaps 100 to 200 times its current size. Some models suggest it could grow even larger during its final stages. At that scale, the sun's outer edge would reach somewhere close to Earth's current orbit. Whether it actually swallows Earth depends on details that scientists are still working out. The the Sun will also lose a significant portion of its mass as it expands, shedding material into space through powerful stellar winds. When a star loses mass, its gravitational pull weakens. A weaker gravitational pull means the planets drift outward. Earth's orbit may shift far enough out that the expanding Sun just barely misses it. But surviving the expansion does not mean surviving in any recognizable form. By that point, Earth's surface will have been scorched beyond anything we can picture. Temperatures will reach thousands of degrees. The atmosphere will have long since been stripped away. The oceans, gone for hundreds of millions of years already, will be a distant memory written only in the rock record. The surface itself may melt. Earth would become a bare, glowing rock drifting through the intense heat of a dying star's outer layers. There is something quietly humbling about this. Earth, which feels so solid and permanent beneath our feet, is part of a much larger story. The ground we walk on, the air we breathe, the water in every river and cloud. All of it exists because the Sun is in a particular phase of its life right now. We live in a window, a long, stable, fortunate window, but a window all the same. Mars and the outer planets will have their own fates. Mars, already cold and thin-aired, will warm as the Sun expands. Its surface temperatures will rise. Whether that warming could ever make Mars briefly more hospitable is a question scientists find genuinely interesting, though the timescales involved are far beyond anything humans could plan around. The gas giants, Jupiter and Saturn, will remain largely intact. Their enormous mass protects them. But their moons, some of which already hold liquid water beneath their icy surfaces, will experience dramatic changes as the Sun's heat reaches further out into the solar system. Every body in the solar system is connected to the Sun by gravity and light and heat. The Sun does not simply shine down on its planets from a safe distance. It shapes them. It holds them. It defines the conditions that make each world what it is. When the Sun changes, it does not change alone. It pulls the whole solar system into a new state, slowly, over timescales so vast they are almost impossible to feel. Earth will not last forever. Neither will Mars or the moons of Jupiter, or the frozen comets drifting at the edge of the solar system. But the atoms that make up all of those worlds, the iron in Earth's core, the carbon in every living thing, the oxygen in the air, those atoms will go on. They were forged in stars long before our sun existed. And when the sun is done, they will find their way into something new. So what is it actually like inside a red giant? The outer layers are vast and cool and slow. But deep inside, the conditions are almost beyond imagining. The interior of a red giant is a place of extremes, where heat and pressure reach levels that have no comparison anywhere on Earth. Start with the core. When a sun-like star swells into a red giant, its core does not expand with the rest of it. The core actually shrinks. It pulls inward, growing smaller and denser as gravity squeezes it tighter and tighter. The outer layers balloon outward, while the heart of the star collapses inward. These two things happen at the same time, pulling in opposite directions, and the result is one of the most dramatic transformations in the universe. That shrinking core becomes extraordinarily hot. The temperature at the center of a red giant's core can reach around 100 million degrees Celsius. That is roughly 7 times hotter than the core of our sun right now. The sun's core today burns at about 15 million degrees. A red giant's core surpasses that by a staggering amount. The numbers are hard to hold in the mind. But the important thing is this: that heat is what drives everything that happens next. At those temperatures, the core is no longer burning hydrogen. The hydrogen is gone. What remains is a dense ball of helium ash, packed so tightly that the atoms themselves are crushed together. The electrons, the tiny particles that normally orbit the center of an atom, are stripped away and squeezed into a state that physicists call electron degeneracy. In this state, the helium core behaves in ways that normal gas does not. It does not expand when it gets hotter. It holds its shape. It becomes, in a sense, rigid. This is one of the strangest and most important properties of matter in the universe, and it sets the stage for something dramatic that will come very soon. Meanwhile, just outside that dense core, a thin shell of hydrogen is still burning. This shell is where most of the star's energy is being produced during the red giant phase. It burns steadily, adding more helium ash to the core below, making the core heavier and hotter with every passing moment. The shell is incredibly thin compared to the vast size of the star around it. And yet, it is doing enormous work, pouring energy outward through layers that stretch for hundreds of millions of kilometers. Those outer layers are, by contrast, almost unimaginably cool for a star. The surface of a red giant sits at around 3,000 to 4,000 degrees Celsius. That sounds hot, but the surface of our sun today is about 5,500 degrees. A red giant is actually cooler at its surface than the sun is right now. The star has grown so large that its energy is spread across a much bigger area. And so each patch of surface glows at a lower temperature. That lower temperature is exactly why red giants appear red and orange rather than yellow or white. The density of those outer layers is also extraordinary in the other direction. They are almost impossibly thin. The outer envelope of a red giant is so spread out that it is closer in density to what we would call a laboratory vacuum on Earth than to anything we think of as solid or liquid. If you could somehow stand inside the outer layers of a red giant, you would not feel surrounded by fire. You would be inside something more like an extremely hot, faintly glowing mist. The material is there, but it is barely there. This contrast defines the red giant. A core so dense and hot that matter itself behaves strangely. An outer envelope so vast and thin it barely qualifies as gas. These two extremes exist inside the same object, connected by layers of churning plasma, each one hotter than the last as you move inward. The star is not one thing. It is a series of nested worlds, each with its own temperature, its own pressure, its own rules, and all of it is moving. Enormous convection currents, the slow rolling motion of hot material rising and cool material sinking, churn through the outer layers of the star. These currents carry energy outward from the burning shell below. They are vast beyond measure. A single convection cell inside a red giant can be larger than the entire distance from the Earth to the Sun. the star breathes in a way. It rolls and turns and carries its heat slowly toward the surface. It is never still. Even in its swollen, aging state, a red giant is alive with motion, right down to its strange and rigid heart. And at the center of all that motion, something waits. The core of a red giant is not burning in the way we usually picture burning. There is no hydrogen left there. The hydrogen is gone, used up long ago. What remains is helium, the ash of all those billions of years of fusion. This helium core sits at the heart of the star, dense and inert, doing nothing. It is just sitting there, growing slowly heavier as the hydrogen shell above it keeps burning and raining more helium ash downward. But the core is not simply resting. It is being squeezed. Gravity never stops pressing inward. As the helium core grows more massive, gravity presses harder. The core shrinks, and as it shrinks, it heats up. This is one of the quiet laws of stellar physics. Compress a gas, and it grows hot. The core has no way to release this pressure through fusion, so it just keeps compressing, keeps heating, keeps building toward something. In most gases, pressure and temperature are linked in a simple way. When a gas heats up, it expands. When it expands, it cools down a little. This natural give and take acts like a safety valve. It keeps things stable. But the helium core of a red giant is so dense that it stops behaving like a normal gas. The electrons inside it, those tiny particles that orbit every atom, are packed so tightly together that they cannot move freely anymore. The core enters a state that physicists call electron degeneracy. In this state, the pressure holding the core up no longer depends on temperature. The safety valve is gone. This matters enormously for what comes next. When the helium core finally reaches about 100 million degrees, something ignites. Helium fusion begins. 3 helium nuclei can fuse together to form carbon. This process is called the triple alpha process because helium nuclei are also known as alpha particles. It is a delicate and precise reaction. The temperatures and pressures required are extreme, but once they are reached, helium begins to burn. Under normal conditions, this new burst of energy would cause cause the core to expand and cool slightly, slowing the reaction down. But the degenerate core cannot expand that way. The pressure does not respond to the new heat. So the fusion accelerates. More heat, more fusion, more heat, more fusion. A runaway reaction building on itself in a matter of seconds, in a very short time, perhaps just a few seconds. The helium core releases an enormous amount of energy. Scientists estimate this energy release is comparable to the entire output of the Milky Way galaxy for those brief moments. This event is called the Helium Flash, and yet you would never see it from the outside. This is perhaps the most quietly astonishing part. All of that energy, that sudden, violent ignition deep inside the star, is absorbed by the outer layers before it ever reaches the surface. The red giant's enormous envelope swallows the flash completely. To any observer watching from a distance, nothing changes. The star looks the same. It glows the same dull red. It shows no sign of the extraordinary event happening at its heart. The helium flash is one of the most powerful events in the life of a sun-like star, and it is entirely invisible. After the flash, the core finally responds. The extreme degeneracy breaks. The core expands slightly, cools to a more stable temperature, and settles into a steady rhythm of helium fusion. The runaway reaction calms. The star finds a new balance. What was a crisis becomes a new kind of life. This transition takes time. Scientists believe the helium flash itself may actually occur as a series of smaller flashes over a period of hours or days, each one slightly less intense than the last, as the core works its way toward stability. The star does not simply snap into its new state. It eases there through a sequence of smaller surges, like a fire finding its steady burn after the first wild flare. There is something deeply quiet about this. The most dramatic moment in the star's middle life happens in total silence, hidden from view, buried under layers of gas so vast that no signal escapes. The universe keeps its secrets well. The star carries this event entirely within itself and then moves on, glowing the same soft red, drifting the same slow drift across the sky. The helium flash is a reminder the most important things are not always the most visible. Sometimes the whole story is happening somewhere you cannot see, in the deep and private heart of things. For a long time, humans had no idea any of this was happening. The stars were just lights. Beautiful, yes. Constant, seemingly. But their inner lives were completely hidden. It took centuries of careful watching, and then a few brilliant leaps of understanding before anyone could say with confidence what a star actually was, let alone what it was doing inside. The story of how we learned about the horizontal branch. The stable phase a star enters after the helium flash begins not with telescopes, but with patience. In the late 1800s, astronomers began photographing the night sky in large numbers. They collected images of thousands of stars and started sorting them by color and brightness. This was slow, painstaking work. Much of it was done by women called computers, hired by the Harvard College Observatory to measure and classify stellar photographs by hand. These women processed hundreds of thousands of stars over decades. Their work built the foundation for almost everything we know about how stars age. One of those women was Henrietta Swan Leavitt. Another was Annie Jump Cannon. Cannon alone classified around 350,000 stars over her career. She developed a system for sorting stars by their surface temperature, using letters that we still use today. Her system revealed that stars came in distinct types, and that those types formed a pattern. The pattern suggested that stars were not random. They were following rules. Something was guiding their lives from birth to death. The next great step came when two astronomers, working independently around 1910, noticed something strange. Ejnar Hertzsprung in Denmark and Henry Norris Russell in the United States both plotted stars on a chart, placing brightness on one axis and color on the other. What they found was not a scattered cloud of random points. Most stars lined up along a smooth diagonal band. A smaller number clustered off to the side, bright but cool and red. These were the giants. The chart they created is now called the Hertzsprung-Russell diagram, and it remains one of the most important tools in all of astronomy. What the diagram showed, though no one fully understood it yet, was that stars move through predictable stages. The main sequence band was where stars like the sun spent most of their lives. The giant branch off to the side was where they went when hydrogen ran out. But there was another cluster of stars on the diagram that puzzled astronomers for years. These stars sat in a roughly horizontal line at a moderate brightness and a bluish-white to yellow color. They did not fit neatly into the main sequence or the giant branch. For decades, no one was quite sure what they were. These were the horizontal branch stars, and understanding them required understanding the helium flash first. That understanding came slowly. Through the middle of the 20th century, as physicists and astronomers began modeling what happens inside stars using mathematics and early computers. In the 1950s and 1960s, scientists could finally simulate stellar interiors with enough detail to trace what happens when a red giant's core ignites helium. The models showed that after the helium flash, the star contracts slightly. Its outer layers pull inward a little. The surface heats up. The star becomes smaller and bluer than it was as a full red giant. It settles into a new, stable phase of life, fusing helium quietly in its core. This is the horizontal branch. The name comes directly from that old diagram. When astronomers plotted these stars, they fell along a roughly horizontal line. The name stuck. It is one of those cases where the name tells you exactly where the thing lives on the chart and nothing more. But the simplicity of the name hides something remarkable. These stars have already survived one of the most violent events in a star's life. They have come through the helium flash and found their footing again. Globular clusters, those ancient, tightly packed balls of stars that orbit our galaxy, turned out to be the best places to study the horizontal branch. Because all the stars in a globular cluster formed at roughly the same time, astronomers could watch many stars at different stages of the same life cycle all at once. It was like looking at a forest and seeing saplings, mature trees, and fallen logs all together. The picture of stellar aging became much clearer. What those clusters revealed was that the horizontal branch is not a single narrow line. It spreads. Some stars sit on the blue end. Some sit on the red end. The exact position depends on how much mass the star shed during its red giant phase. Small differences in mass lead to big differences in where a star lands. The horizontal branch turned out to be a record of each star's individual history, written in color and light. So the horizontal branch tells a story. Each star's position on it reflects choices made long before, during the red giant years. But that story is not finished yet. The horizontal branch is not the end. It is only a pause. A star on the horizontal branch is burning helium in its core. That helium is being fused into carbon and oxygen, slowly and steadily. The star has found a kind of balance again. But helium, like hydrogen before it, does not last forever. And when the helium in the core finally runs out, something surprising happens. The star does not simply stop. It swells again. This is the part that catches people off guard. Most of us imagine a star aging in one long, smooth decline. We picture it growing once, slowly dimming and fading away. But that is not what happens. Sun-like, stars swell into red giants twice. The second swelling is in some ways even stranger than the first. When the helium in the core is gone, the core contracts again, just as it did when the hydrogen ran out. The heat from that contraction spreads outward. It reaches a thin shell of helium just outside the core, and that shell begins to burn. Above it, a shell of hydrogen starts burning too. The star now has two separate burning shells, layered like the rings of a tree, each one feeding energy outward. The outer layers of the star respond by expanding once more. The star grows large and red again, climbing back toward the top of the brightness scale. What makes this second expansion so strange is how much more dramatic it can be. During this phase, the star can grow even larger than it did the first time. Some stars in this second red giant phase reach sizes that are genuinely hard to picture. A star that once fit comfortably inside the orbit of Venus might now stretch past the orbit of Mars. The outer layers become so loosely held that they barely feel the pull of the core at all. The grip of gravity weakens at the surface as the star grows. This matters because it means the star begins to lose mass at a much faster rate. During the first red giant phase, the star shed material slowly, carried away by a gentle stellar wind. During this second expansion, that wind grows stronger. The star begins to exhale great streams of gas and dust into the space around it. Scientists estimate that a star in this phase can lose mass at a rate millions of times faster than our sun loses mass today. It is not an explosion. It is more like a long, slow breath that never quite stops. Here is something that surprises even astronomers who have studied stars for decades. The burning shells during this second phase are not stable. They pulse. The helium shell does not burn at a steady rate. Instead, it builds up helium from the hydrogen shell above it. And then, that helium ignites all at once in a sudden burst of energy. These bursts are called thermal pulses, and they happen over and over again, separated by thousands of years of quiet. Each pulse sends a wave of energy through the star's outer layers. Each one pushes more material outward into space. During these thermal pulses, something remarkable happens deep inside the star. The mixing of material between layers can carry carbon, oxygen, and other elements up toward the surface. Elements that formed deep in the core through millions of years of nuclear burning get dredged upward. This process, which astronomers call dredge-up, brings the products of nuclear fusion to the outer layers of the star. The star is, in a sense, turning itself inside out, slowly and repeatedly. This matters far beyond the star itself. Those outer layers, now rich with carbon and oxygen and other heavy elements, are being pushed into the surrounding space with every pulse, every gust of stellar wind. The material does not disappear. It drifts outward, cooling slowly, forming tiny grains of dust. Some of the carbon condenses into particles that look, under the right conditions, like microscopic diamonds. The space around a dying star in this phase can fill with a faint, glittering cloud of dust and gas. What seemed like a simple ending turns out to be a rich and complicated process, full of layers and surprises. The star that once burned hydrogen quietly for billions of years, is now, in its final chapters, doing some of its most complex work. It is building the raw material that will one day drift through the galaxy, cool and settle, and become part of something new. This phase of a star's life has a name. Astronomers call it the Asymptotic Giant Branch, or AGB for short. It is the second time a sun-like star swells into a giant, and in many ways it is the more dramatic of the two. The star has already burned through its hydrogen. It has already burned through most of its helium. Now it sits on the edge of something new, pulsing and breathing and shedding material into the dark. The word asymptotic comes from mathematics. It describes a line that curves closer and closer to another line, but never quite touches it. In stellar terms, the AGB star is climbing a path on an astronomer's chart that curves steeply upward, growing brighter and larger with each passing pulse cycle. The star is approaching something it cannot hold back. It is moving slowly but surely toward the end. What makes the AGB phase so remarkable is not just what is happening inside the star. It is what the star is giving away. During this phase, a sun-like star sheds an enormous amount of its own mass. Over tens of thousands of years, the star loses material steadily through powerful stellar winds, streams of gas and dust flowing outward in all directions. Some AGB stars lose mass at a rate that would seem impossible for a quiet, middle-aged star like our sun. They are generous in their dying, and what they give away matters deeply to the rest of the galaxy. The material streaming off an AGB star is not plain hydrogen. It is enriched. It carries carbon, oxygen, nitrogen, and heavier elements that were forged in the star's core and carried upward through the dredge-up process. These elements drift outward into the surrounding space, cooling as they travel. They mix with the thin clouds of gas that already float between the stars. Over time, that mixture becomes the raw material for new stars, new planets, and new chemistry. This is one of the most important connections in all of astronomy. The AGB phase links the life of one star to the birth of another. It links the deep interior of a dying sun to the outer edges of a growing solar system, perhaps one that will not form for another billion years. The carbon in your pencil, the oxygen in your lungs, the nitrogen in the air around you right now. Much of it passed through a star in this exact phase, long before our sun was born. The dust grains that form in the cool outer layers of an AGB star are especially significant. They are tiny, far smaller than a grain of sand, but they are solid. They are the first solid particles to form from stellar material in the cold of space. When these grains drift into a cloud of gas, and that cloud begins to collapse under gravity, the dust grains act as seeds. Gas molecules cling to them. Ice coats them. Over millions of years, they clump together and grow. This is how the building blocks of planets begin. Our own solar system carries evidence of this. Scientists have found tiny grains of material inside ancient meteorites, rocks that fell to Earth from space, that formed inside AGB stars before our sun existed. These grains are older than the sun itself. They are called presolar grains, meaning they came before our solar system. Holding a meteorite that contains them is, in a quiet way, holding a piece of a star that lived and died before our own star was born. The AGB phase also connects to the chemistry of life. Carbon is the backbone of every living thing on Earth. Every cell, every strand of DNA, every leaf and shell and bone is built around carbon atoms. AGB stars are among the most productive sources of carbon in the entire galaxy. They are, in a very real sense, carbon factories. Without them, the chemistry that life depends on would be far less common in the universe. There is something deeply settling about this picture. The universe does not waste anything. A star that has burned for billions of years does not simply go dark and disappear. It spends its final phase doing some of its most generous work, pouring its hard-won elements back into the galaxy. The material flows outward, cools, and waits. It drifts through space for millions of years, patient and quiet, until gravity calls it together again. One star's ending becomes another star's beginning. One world's dust becomes another world's ground. The AGB star is not just dying. It is passing something forward, and the galaxy slowly and silently receives the gift. The AGB star does not pass this gift forward quietly. In its final phase, it is a restless, breathing thing. It pulses. It swells and contracts, like a slow and enormous heartbeat. These pulsations are not subtle. They happen over months or years, and they change the star's brightness as they go. When the star expands, it grows dimmer and cooler. When it contracts, it brightens again. Astronomers can watch this rhythm from Earth, tracking the rise and fall of light across hundreds of days. These pulsating stars have a name. They are called Mira variables, after a star called Mira in the constellation Cetus. Mira itself was one of the first variable stars ever recorded. Ancient astronomers noticed it appearing and disappearing in the sky over a cycle of roughly 332 days. They did not know what it was. They called it the Wonderful. Today, we know Mira is an AGB star in its late stages, swelling and shrinking, breathing in and out on a schedule that has continued for thousands of years. Its brightness changes by a factor of more than 1,000 between its dimmest and brightest points. That is an extraordinary range for a single star. The pulsations do more than change the light. They drive something powerful outward from the star's surface. As the outer layers expand and contract, they push material upward into the star's atmosphere. Dust grains form in this cooler, outer region, tiny solid particles made of carbon or silicate minerals. Then something remarkable happens. The star's own light pushes against those dust grains. Radiation pressure, the gentle but steady force of light itself, drives the dust outward, and the dust carries the gas along with it. This is how a stellar wind begins. A stellar wind is a slow but constant outflow of gas and dust from a star's surface. The sun has a stellar wind too, a thin stream of charged particles that flows outward through the solar system. But the wind from an AGB star is something far more powerful. It is not a thin stream. It is a flood. An AGB star can lose the equivalent of the Earth's mass every single year, carried away in this slow, thick outflow. Over thousands of years, the star loses a significant portion of its total mass this way. This mass loss is one of the most important processes in the life of a dying star. It shapes what comes next. The more mass a star sheds during the AGB phase, the smaller and less massive its core becomes by the time the outer layers are gone. That core mass determines what kind of object the star leaves behind. For sun-like stars, the answer is a white dwarf, a dense, glowing remnant about the size of Earth. But the path to that ending runs directly through these pulsations and winds. The wind does not flow out evenly in all directions. Astronomers have found that AGB winds often form thick shells of gas and dust around the star, layer after layer, like the rings inside a tree. Each pulse pushes out a new wave of material. These shells expand slowly outward into the space around the star, growing wider and thinner over thousands of years. When astronomers look at AGB stars through infrared telescopes, which detect heat rather than visible light, they can sometimes see these shells glowing softly in the dark. They look like faint, nested rings surrounding a dim red point of light. The wind also carries with it all the elements the star has spent its life creating: carbon, oxygen, nitrogen, silicon, and dozens of other atoms flow outward in this slow river of gas and dust. They cool as they travel. Some of them bond together into molecules. Some form tiny solid grains. These grains are the seeds of future planets. The same kind of dust that now drifts away from a distant AGB star may one day fall into a collapsing cloud of gas, mix with other material, and eventually become part of a rocky world orbiting a young star. The pulsations continue for thousands of years. The star breathes in and out, slower and slower, losing more of itself with each cycle. It is not a violent process. There is no explosion, no sudden collapse. It is gradual and patient, the way a candle burns down rather than blows out. The star is changing. It has been changing for billions of years, and now it is entering the final stages of that change. The outer layers are growing thinner. The core is growing hotter. Something is building quietly at the center of all this slow motion. is preparing, without knowing it, to let go. And then, slowly, the letting go begins. The outer layers of the star have been loosening for thousands of years. The pulsations have pushed them a little farther out with each cycle. The stellar wind, that constant outward flow of gas, has been carrying material away into the dark. But now something shifts. The star's grip on its own outer shell grows weaker. The layers drift away more freely. What was once a slow river becomes something closer to a tide going out and never quite coming back. This process is called mass loss. It is exactly what it sounds like. The star is losing its own mass, its own material, out into the space around it. A star like our sun holds onto its gas through gravity. But as the star swells and its outer layers cool and thin, that grip loosens. The gas at the very edge of the star is barely held at all. The stellar wind carries it away, gram by gram, year by year, across thousands and thousands of years. The amount of mass a star can lose this way is staggering. An AGB star, one of these ancient pulsing giants in its final stage, can shed anywhere from 1/10 to more than half of its total mass during this long, slow process. All of that material, all of those atoms, the star spent billions of years building, drifts outward into a growing shell of gas and dust surrounding the star like a soft cocoon. And here is where light enters the story in a quiet and beautiful way. The gas and dust in that expanding shell are not invisible. They catch the light from the star still burning at the center. The dust grains, those tiny solid particles that formed as the gas cooled during its outward journey, absorb the star's light and then re-emit it. They glow, but they glow in a kind of light that human eyes cannot see. They glow in infrared light, which is the warm, invisible light that carries heat. Astronomers use special telescopes that can detect infrared light. And when they point those telescopes at AGB stars surrounded by thick shells of dust, they see something remarkable. The star itself may be nearly hidden behind its own shed material, but the shell around it blazes in infrared, warm and glowing, like an ember wrapped in smoke. Some of these stars are so wrapped in their own dust invisible in ordinary light. They are called infrared stars, and they are among the brightest objects in the infrared sky. The dust shell acts like a filter, swallowing the visible light and releasing it again as heat. The star is still shining. Its light is just being translated into a different language. Not all of the light disappears, though. Some of it escapes, and the colors it carries tell a story. The dust grains scatter light the way tiny particles always do, favoring certain colors over others. Shorter wavelengths of light, the blues and violets, scatter more easily. Longer wavelengths, the reds and oranges, pass through more freely. This is the same reason sunsets on Earth turn red and gold when light travels through more of the atmosphere. The physics is the same. A thick shell of dust around a dying star reddens the light that passes through it, just as the air above the horizon reddens the setting sun. So when astronomers look at these stars through ordinary telescopes, the ones that do show through their dust shells often appear deeply red, not the red of a cool surface, though that is part of it too, but a reddened, filtered red, the color of light that has traveled through a veil of its own making. There is something quietly moving about this. The star is shedding the very material that now colors its own light. It is surrounded by itself. The atoms it forged, the dust grains that formed from those atoms, now wrap around it and change how it appears to the universe. The star is, in a sense, wearing its own history, and all of this is still gentle, still slow. The shell expands outward at speeds of roughly 10 to 30 kilometers per second, which sounds fast, but is measured against distances so vast that the shell takes thousands of years to spread even a fraction of a light year from its source. The star at the center continues to burn, continues to pulse, continues to lose itself into the surrounding dark. The cocoon grows. The core grows hotter still. The outer layers thin to almost nothing. Something is about to change in a more visible way. The star is nearly ready to show the universe what it has been building toward all this time. And then something shifts. The core of the star has been growing hotter for thousands of years. It has been contracting, squeezing, building pressure. The outer layers have been drifting away, thinning like fog burning off in the morning. And now the core reaches a temperature of roughly 100,000 degrees. At that point, something remarkable begins. The remaining outer shell of gas is no longer just drifting. It is being pushed. The hot core begins to pour out a fast, powerful stream of particles. This is called the stellar wind. And at this stage, it is far stronger than anything the star produced in its earlier life, where the slow wind of the giant phase moved at 10 to 30 kilometers per second. This new wind screams outward at speeds of thousands of kilometers per second. It catches the slow-moving shell that was shed before it. It slams into it. It compresses it. It shapes it. This is how a planetary nebula is born. The name is a little misleading. Planetary nebulae have nothing to do with planets. Early astronomers, looking through small telescopes, saw these glowing clouds and thought they looked a little like the round disk of a planet. The name stuck. But what they were really seeing was something far more dramatic. They were seeing a dying star's final breath made visible. The compressed shell of gas begins to glow. The intense radiation pouring from the hot core strikes the surrounding gas and strips electrons loose from atoms. This process is called ionization. When those electrons eventually fall back into their atoms, they release energy as light. The nebula lights up from within. It shines not because it is burning, but because it is being energized by the star at its center. Now, here is where the sounds come in. Space itself carries no sound. There is no air to carry a wave. But the events happening inside a forming planetary nebula produce real physical vibrations, and scientists have found ways to hear them. Instruments on spacecraft and ground-based observatories detect pressure waves, shock waves, and rhythmic pulses moving through the gas. These signals can be converted into audio, shifted into ranges the human ear can detect. What they reveal is extraordinary. The collision between the fast wind and the slow shell creates a shock front, a place where gas is suddenly compressed and heated. That compression travels as a wave. Scientists have translated similar shock events from other stellar objects into sound, and what they hear resembles a deep, rolling boom, low and slow, distant thunder heard from far away. The gas does not explode all at once. It is pushed and shaped over thousands of years, and the pressure waves ripple through it in long, slow pulses. The star itself, the hot core now exposed at the center, also vibrates. Many of these cores pulse with a rhythm. They expand and contract slightly over and over, and those pulses send waves outward into the surrounding gas. Scientists studying similar objects have recorded these rhythms and converted them into tones. They sound like a slow, deep hum, steady and ancient, like something breathing in the dark. There is also something that sounds almost like wind. The fast, stellar wind rushing outward at thousands of kilometers per second creates a continuous stream of charged particles. When data from this kind of flow is converted to audio, it produces a long, rushing hiss, not unlike the sound of wind through tall grass on a quiet evening. It is constant. It is the sound of the star still giving itself away. What makes all of this so striking is the scale. The nebula forming around a dying star can stretch for a light year or more in every direction. A light year is roughly 9.5 trillion kilometers. The gas spreading across that distance is thin, far thinner than the best vacuum humans can create in a laboratory. And yet it glows. It carries waves. It holds the record of everything the star went through. Each planetary nebula is shaped differently. Some form perfect spheres. Others stretch into long, narrow cylinders. Some look like butterflies, with two great lobes of glowing gas spreading out from a bright center. The shapes depend on how the star rotated, whether it had a companion star nearby, and how the winds interacted with the gas. Everyone is different. Everyone is a record of a particular star's particular life. The universe is full of these glowing clouds. Thousands have been catalogued. Each one marks the place where a star like our sun once stood. Each one is still moving, still expanding, still carrying its slow vibrations outward into the quiet dark. Those glowing clouds come in colors that no painter could have planned. The light from a planetary nebula is not white. It is not a single shade. It arrives in precise, distinct colors, and each color tells a story about the gas that made it. Hydrogen glows red. Oxygen glows blue-green. Nitrogen glows deep red. These colors are not random. They follow exact rules set by the structure of atoms themselves. When energy from the hot central star strikes a gas atom, it pushes electrons, the tiny particles orbiting the atom's core, up to a higher energy level. When those electrons fall back down, they release that energy as light, and the color of that light depends entirely on which atom it came from and how far the electron fell. Hydrogen always releases the same shade of red. Oxygen always releases the same blue-green. The colors are fixed. They are written into the structure of matter itself. This is how astronomers can look at a glowing nebula from thousands of light years away and know exactly what it is made of. The colors are a kind of language. Scientists call this process spectroscopy, reading the light to identify the elements. Every element in the universe has its own unique set of colors, like a fingerprint. No two elements produce the same pattern. This means that a telescope pointed at a distant cloud of gas can read its chemistry the way you might read a page of text. The math behind this is elegant in its simplicity. The energy of a photon, a single particle of light, is directly tied to its wavelength, which is what determines its color. Shorter wavelengths carry more energy and appear blue or violet. Longer wavelengths carry less energy and appear red. The relationship between energy and wavelength follows a clean, precise equation discovered by the physicist Max Planck in the early 1900s. That same equation governs every photon of light in the universe, from the glow of a dying star to the beam of a flashlight. The shapes of Planetary, nebulae, follow their own kind of mathematics too. A star that rotates slowly tends to shed its outer layers in a more even sphere. A star that spins faster flings more gas outward along its equator, creating a flattened disk shape. When a second star orbits nearby, its gravity pulls the expanding gas into asymmetric forms. Those butterfly shapes, those long lobes, those twisted spirals. The geometry of each nebula is a direct record of the forces that shaped it. Every curve and angle has a cause. most studied planetary nebulae in the sky have been measured with great precision. The ring Nebula in the constellation Lyra sits about 2,500 light-years from Earth. It spans roughly 1 light-year across. Its central white dwarf, the small, dense remnant of the original star, burns at around 120,000 degrees Celsius. That is more than 20 times hotter than the surface of our sun. The intense radiation from that tiny star is what makes the surrounding gas glow so vividly. The Helix Nebula, one of the closest planetary nebulae to Earth, at about 650 light-years away, stretches nearly 3 light-years across. If you placed it where our sun sits, its outer edge would extend well past the orbit of Pluto. It looks, from our angle, like a great eye staring out of the dark. Ancient astronomers had no way to know what it was. Now we understand it completely. It is the shed skin of a star that lived and died before our own sun had even formed. The numbers involved in these objects are almost too large to hold in the mind. But there is something calming about them. The universe runs on rules that do not change. The same physics that governs a hydrogen atom on Earth governs one in a nebula 3,000 light-years away. The same equations that describe how gas expands in a laboratory describe how it expands across a light-year of empty space. The scale changes. The rules do not. There is a kind of quiet reassurance in that. The universe is vast and ancient and full of forces far beyond anything human. And yet it is consistent. It is predictable. The colors of a dying star can be calculated before a telescope ever looks at them. The shape of a nebula can be modeled from the physics of rotating gas. The distance to a glowing cloud can be measured using the same geometry a student learns in school. The universe is enormous, but it is not chaotic. It is precise. It is orderly. And in that order, there is something that feels, in the quietest possible way, like peace. When a star like our sun finishes its long life and sheds its outer layers, what remains is something almost impossibly small compared to what came before. The white dwarf left behind is roughly the size of Earth, yet it holds about half the mass of the original star. means something the size of our entire planet is packed with the weight of half a sun. The density is extraordinary. A single teaspoon of white dwarf material would weigh roughly 5 tons on Earth. And yet, for all that density, for all that mass compressed into such a small space, the white dwarf is fragile in its own way. It no longer burns fuel. It no longer generates heat through fusion. The process of smashing atoms together that powered the star for billions of years. It simply glows with the heat it already has. Slowly, over an almost unimaginable stretch of time, it cools. It radiates that stored warmth out into the cold dark of space, like an ember pulled from a fire and set on a stone floor. The white dwarf survives not because of any ongoing process inside it, but because of something called electron degeneracy pressure. That is the force that comes from electrons, the tiny particles that orbit atomic cores, being packed so tightly that the laws of quantum physics, the rules that govern the very smallest scales of matter, refuse to let them be squeezed any further. It is a kind of pressure that does not depend on temperature. It does not fade as the star cools. It simply holds. The white dwarf is supported by the rules of physics themselves. But that support has a limit. Scientists have calculated that if a white dwarf ever gained enough mass, roughly 1 4/10 times the mass of our sun, that electron pressure would fail. The star would collapse. This limit is called the Chandrasekhar limit, named for the physicist Subrahmanyan Chandrasekhar, who worked out the mathematics in the 1930s. He was in his early 20s when he did it. The universe had been operating by that rule for billions of years before anyone on Earth knew it existed. This is where the fragile balance becomes something worth sitting with quietly. The white dwarf that our sun will one day become will sit just below that limit. It will be stable. It will cool for billions, perhaps trillions of years. But if it had a companion star nearby, one close enough to slowly donate mass across the gap between them, the balance could tip. Enough added mass, and the white dwarf would cross that threshold. The result would be a thermonuclear explosion, a type Ia supernova, one of the most powerful events in the known universe. The same object that spent billions of years gently cooling, could, under the right conditions, detonate with the brightness of an entire galaxy. The conditions that prevent this from happening to our sun's future remnant are not dramatic. They are simply the result of our sun being a single star, without a close binary companion feeding it extra mass. One variable, one difference, and the outcome changes entirely. This kind of precise balance shows up everywhere when you look at the conditions that allowed life to form here on Earth. Our planet sits at a distance from the sun where liquid water can exist on the surface. A little closer, and the oceans would boil away. A little farther, and they would freeze solid. Scientists call this the habitable zone. Earth sits comfortably within it, but not by an enormous margin. The precision is quiet and easy to overlook. Our atmosphere, the thin layer of gas that wraps around the planet, is another piece of this careful arrangement. It is only about 100 kilometers thick, which sounds like a lot until you consider that Earth's diameter is nearly 13,000 kilometers. The atmosphere is, in proportion, thinner than the skin of an apple. And yet, it holds in warmth, filters out harmful radiation from the sun, and carries the oxygen that every breath depends on. The magnetic field generated deep inside Earth's iron core shields the surface from the solar wind. The stream of charged particles the sun constantly sends outward. Without that invisible shield, the solar wind would slowly strip the atmosphere away, the way it stripped the atmosphere from Mars long ago. Mars lost its magnetic field. It lost its air. It became a cold, dry, nearly airless world. Everything that makes Earth what it is depends on a chain of conditions, each one resting on the one before it. The right star, the right distance, the right size, the right interior, the right atmosphere. Each piece holds the others in place. Remove one, and the whole arrangement shifts into something unrecognizable. What gets left behind when a red giant finally sheds its outer layers is something remarkable. It is small. It is dense. It is quiet. And it will outlast almost everything else in the universe. It is called a white dwarf, and it is the final form of nearly every sun-like star that has ever burned. A white dwarf is the exposed core of what was once a star. All the outer layers have drifted away into the surrounding nebula. What remains is a sphere roughly the size of Earth, but packed with a mass close to that of the Sun. A single teaspoon of white dwarf material would weigh several tons if you could somehow bring it here. The gravity at its surface is about 300,000 times stronger than the gravity you feel right now. And yet, for all that density, a white dwarf produces no new energy. It no longer fuses anything. The nuclear fires that burned for billions of years have gone out. What you are left with is an object that simply glows from the heat it still holds inside. The way a stone pulled from a fire still radiates warmth long after the flames are gone. Scientists call this stored heat, and it is the only thing keeping a white dwarf bright. This is where the mystery begins. A white dwarf cools very, very slowly. The process takes billions of years, far longer than the current age of the universe. That means every white dwarf that exists today is still warm. Not one has had enough time to cool completely. Scientists have never observed a fully cooled white dwarf because the universe is not old enough to have made one yet. They call the theoretical end state a black dwarf, a cold, dark, inert sphere drifting silently through space. But no black dwarf has ever been seen. None exists yet, as far as we know. This creates a fascinating gap in our understanding. We can model what a black dwarf should look like. We can calculate how long the cooling should take. Somewhere between 1 and 10 quadrillion years. A number so large it barely fits inside the imagination. But we cannot confirm any of it through observation. We are working from physics alone, from equations and predictions, trusting that the math holds even when the evidence is still billions of years away from existing. There is another open question that scientists find deeply interesting. White dwarfs do not all cool at the same rate. Some cool faster than expected, some slower. The reasons are not fully understood. The composition of the white dwarf matters, whether it is made mostly of carbon and oxygen, or whether it contains more exotic elements. The presence of a thin hydrogen or helium atmosphere on the surface also affects how heat escapes. Small differences in structure lead to surprisingly large differences in behavior over time. Some white dwarfs also pulse. They expand and contract slightly, vibrating in slow, rhythmic waves. Scientists use these vibrations the way a doctor uses a heartbeat, listening carefully for what they reveal about the interior. This field of study is called astrocosmology, the science of reading a star's inner structure through its vibrations. White dwarfs have given researchers some of their clearest windows into what lies beneath the surface of a stellar remnant. And still, the full picture is not complete. There is also the question of what happens when a white dwarf is not alone. Many stars exist in pairs, two stars orbiting each other in a slow, gravitational dance. When one becomes a white dwarf and the other is still an active star, the white dwarf can begin pulling material from its companion. This stolen gas builds up on the surface. If enough accumulates, it can trigger a sudden explosion called a nova, a burst of light so bright it can briefly outshine an entire galaxy. In rare cases, if the white dwarf pulls in too much mass and crosses a certain threshold, it can detonate completely in an event called a type Ia supernova. These explosions are so consistent in their brightness that scientists use them as measuring tools to calculate distances across the universe. A dead star becomes a ruler for measuring the cosmos. What is striking about all of this is how much remains open. The white dwarf is not a solved problem. It is a slowly cooling question mark, drifting through the dark, still holding secrets that our instruments are only beginning to read. The universe does not give up its answers easily. It asks us to be patient, to keep watching, to keep listening. And in that patience, there is something quietly wonderful. The story of a star does not end cleanly. It lingers, it cools, it waits. The gas that a dying star breathes out does not simply vanish into the dark. It travels, it spreads, it becomes something new. When a sun-like star sheds its outer layers and forms a planetary nebula, that glowing shell of gas begins expanding outward into space. It moves slowly at first, then faster as it pushes into the thin material already drifting between the stars. Over thousands of years, The shell grows wider and wider, like a ripple spreading across still water. Eventually, after tens of thousands of years, the shell becomes so thin and so spread out that it dissolves completely into the space between stars. The nebula disappears, but the gas does not. That gas becomes part of what scientists call the interstellar medium. The interstellar medium is the vast, thin mixture of gas and dust that fills the space between all the stars in a galaxy. It is not empty space. It is a slow, drifting ocean of material, incredibly thin by any measure we use on Earth, but present everywhere. And it is constantly being refreshed every time a star dies and releases its outer layers. It adds new material to this ocean. The dying star gives back what it once gathered. The gas released by a red giant is not the same gas the star was born from. The star has changed it. Deep inside the star, nuclear fusion built new elements out of simpler ones. Hydrogen became helium. Helium became carbon and oxygen. These newly made elements ride outward with the expelled gas and mix into the interstellar medium. The space between stars slowly grows richer in carbon and oxygen because of stars like our sun. Carbon and oxygen are not minor additions. Carbon is the backbone of all life on Earth. Every living thing, every cell, every strand of genetic material is built around carbon atoms. The oxygen we breathe was forged inside stars. When a sun-like star dies and releases these elements, it is not just ending its own story. It is writing the opening lines of stories that have not yet begun. Over millions of years, the interstellar medium shifts and stirs. Gravity is always at work, pulling denser patches of gas together. Shock waves from distant explosions can compress regions of the medium, nudging gas clouds into collapse. Slowly, over enormous stretches of time, pockets of gas grow dense enough to begin forming new stars. The material from old, dead stars gathers into new ones. The cycle turns again. The carbon and oxygen that our sun will one day release will drift through space for a very long time. Scientists estimate that the interstellar medium recycles its material roughly every few 100 million years, though the exact timescale varies depending on where in the galaxy you are looking. The gas from our sun's eventual death will not sit still. It will move, mix, and eventually find its way into something new. Perhaps a new star. Perhaps a planet forming around that star. Perhaps something more. The planetary nebula itself, before it fades, leaves a faint trace in the structure of the galaxy. The expanding shell sweeps up surrounding gas as it grows, creating thin walls of compressed material. These walls can persist for a long time, shaping the local environment around the white dwarf left behind. The dead star does not just sit quietly. Even in death, it reshapes the space around it. There is something worth sitting within all of this. The gas that leaves a dying star carries the memory of everything that star experienced. It carries the carbon built during the Helium Flash. It carries the oxygen made during the star's long middle life. It carries trace amounts of heavier elements dredged up from deep inside during the star's final pulsing years on the Asymptotic giant branch. All of that history travels outward, encoded in atoms, drifting through the dark. In 1 billion years, the material our sun releases will be unrecognizable as having come from our sun at all. It will have mixed with gas from thousands of other stars. It will have been compressed and heated and cooled again. But the atoms will still be there. Carbon atoms forged in our sun's core will persist. They do not wear out. They do not decay. They simply become part of whatever comes next. The universe is always in the middle of becoming something. The gas expelled from a dying star is not waste. It is raw material. It is the universe gathering itself, rearranging, preparing. Every ending feeds a beginning that is still too far away to see. And somewhere in the dark, that process is already underway. Somewhere in the dark, a cloud of gas is slowly pulling itself together. It is cold and vast and very quiet. It drifts between the stars, barely visible, lit only by the faint glow of distant suns. But inside that cloud, gravity is already working. Atom by atom, the gas is drawing inward. The cloud is beginning to collapse. And when it finally does, a new star will be born. That cloud is not empty space made solid. It is not new material. every atom inside it has a history stretching back billions of years. Some of those atoms were forged in the cores of stars that lived and died long before our sun ever formed. The carbon atoms came from red giants, built during the slow burn of helium fusion deep inside a dying star. The oxygen atoms were made even earlier, during the long, stable middle life of stars like ours. The nitrogen, the neon, the trace amounts of silicon and sulfur, all of it was cooked inside stellar cores, then released into space when those stars shed their outer layers or exploded at the end of their lives. The universe does not make atoms easily. It took billions of years of stellar birth and death to build up the supply of elements we see today. The very first stars, born not long after the Big Bang, had almost nothing to work with. They were made almost entirely of hydrogen and helium, the two simplest elements, the only ones the Big Bang itself produced in large amounts. Those first stars burned fast and hot. When they died, they scattered heavier elements into space for the very first time. Each generation of stars that followed was born from richer material than the one before. Our sun is a third-generation star, or possibly even later. The gas cloud that formed it already carried the legacy of many previous stellar lives. The iron in Earth's core, the calcium in our bones, the oxygen in every breath we take, none of it was made here. It was made somewhere else, in the heart of a star that no longer exists. And it traveled through space for millions of years before it became part of us. That is not a metaphor. It is chemistry. The calcium atom in a human bone is the same calcium atom that was once fused inside a stellar core. It passed through a dying star's outer layers, drifted through a nebula, collapsed into a new solar system, settled into a rocky planet, and eventually became part of a living thing. The atom did not change. Only its address did. Red giants are especially generous contributors to this process because they expand so slowly and shed their layers through stellar winds rather than violent explosions. They release their material gently over thousands of years. That material spreads wide and mixes thoroughly with the surrounding gas. Planetary nebulae, those glowing shells of expelled gas, star's life, are among the most chemically rich structures in the galaxy. They seed the space around them with carbon, nitrogen, and oxygen in concentrations far higher than the average interstellar cloud. Scientists estimate that a significant portion of the carbon in the Milky Way was released by stars on the asymptotic giant branch. That final pulsing phase before a sun-like star sheds its outer layers entirely. That means the carbon in your body, the carbon in every living thing on Earth, very likely passed through a red giant at some point in its long history before it ever reached our solar system. There is something deeply settling about that. We are not separate from the stars. We are made of them. The same processes that govern the life and death of a star also govern the chemistry of life on Earth. Stars fuse hydrogen into helium to stay alive. Our cells burn glucose to stay alive. Both are just energy being released from stored chemical potential. The universe uses the same basic logic at every scale, and the cycle continues. The gas our sun will one day release will drift outward into the galaxy. It will cool and mix and wait. In a few billion years, some of it may collapse into a new star. That star may have planets. Those planets may have oceans. Those oceans may have life. And that life, if it ever looks up at the night sky, will be looking out through eyes made of atoms that were once inside our sun. The universe keeps nothing for itself. Everything it builds, it eventually gives back. And what it gives back, it uses to build something new. And so we arrive at the end of this long, quiet night of learning. The sun is about 4.5 billion years old. It sits roughly halfway through its life as a stable, hydrogen-burning star. For another 5 billion years or so, it will rise and set just as it does today. It will warm the oceans. It will drive the winds. It will feed the plants that feed everything else. The sun is not finished, not even close, but one day it will be. And when that day comes, the sun will not simply go dark. It will swell into a red giant, shed its outer layers in a slow and glowing cloud, and leave behind a white dwarf no larger than Earth. That white dwarf will cool over billions of years, fading from white to yellow to orange to red. eventually to a cold, dark object called a black dwarf. Scientists believe no black dwarfs exist yet anywhere in the universe. The universe is not old enough. Even the oldest white dwarfs are still glowing. There is something calming in that. The universe is still young. The stars are still burning. The story is nowhere near its end. Our sun is one star among roughly 200 billion in the Milky Way galaxy alone. And the Milky Way is one galaxy among perhaps 2 trillion in the observable universe. That number is almost impossible to hold in your mind. 2 trillion galaxies, each containing hundreds of billions of stars, each star with its own life, its own arc, its own slow burning and eventual release. The universe is not empty. It is full, almost beyond imagining, of light and heat and motion and time. And yet, from here, on this small blue planet, the night sky looks peaceful. The stars look still. They hang there like distant lanterns, quiet and steady. And it is easy to forget that each one is a furnace the size of 1,000,000 Earths, fusing atoms together at its core, holding itself up against its own gravity through sheer force of energy. What looks like stillness is actually a perfect, ongoing balance. Gravity pulling inward, energy pushing outward. A balance that holds for billions of years. The sun will hold that balance for billions more. And while it does, life continues here. The oceans rise and fall with the tides, pulled gently by the moon. The moon itself is slowly drifting away from Earth, about 1.5 inches farther each year. The continents are still moving, carried on slow plates of rock that grind and shift over millions of years. The atmosphere breathes in and out with the seasons. Everything is moving. Everything is changing. And yet, from a human lifetime, it all feels wonderfully, peacefully still. That stillness is a gift. It lets us sleep. It lets us dream. The carbon in your body was made inside a star that died before the sun was born. The iron in your blood was forged in a stellar core and scattered by an explosion billions of years ago. The water in your cells has cycled through oceans and clouds and ice sheets and rivers for billions of years before it ever reached you. You are not a visitor to this universe. You are a part of it, a temporary, intricate, astonishing part of it. The sun knows nothing of this, of course. It does not think or feel or wonder. It simply burns, steady and faithful, the way it has for 4.5 billion years. But we can wonder. We can look up at the night sky and feel the full weight of what we are part of. A galaxy turning slowly in the dark. A star warming a small planet. A planet holding its oceans close. And somewhere on that planet, someone lying still, breathing slowly, letting their eyes grow heavy. The universe is very large. You are very small. And somehow, that is not frightening. It is a comfort. You are held inside something ancient and enormous and still going. The same stars that were burning when the first living things appeared on Earth are still burning now. The same laws of physics that shaped the first atoms still shape everything you can see and touch and feel. Nothing is wasted here. Not a single atom. Not a single moment of light. The sun will rise again tomorrow, just as it has for billions of years. And tonight, beneath a sky full of stars, you can rest. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.